In this video, we are going to see how to simplify a logic expression using the technique of the Carnot map. In fact, the Carnot map method is just a graphical method to do the same algebraic simplification we have seen in the previous example. Only that using the Carnot map, it's easier to see which minterms and which implicants can be simplified. Okay, so we'll start by drawing a Carnot map for this function for variables Carnot map. You can skip this part while I draw the map. Okay. Now, when you sort the variables in the Carnot map, you can sort them as you prefer, but depending on the where you put the variables, you will have your minterms in your map. So with variables like this, 1, 0, then we will have minterm 0 here, minterm 1 here, minterm 2 here, minterm 3 here, and so on. Okay, so yes, we just copy the minterms from the expression as the sum of minterms to the map. I have the function is 1 here, is 1 here, has minterm 4, 5, 6, 7, 8, 9. 8, 9 has minterm 10, 11, 12, 13, 14, 15. Okay? So this is the Carnot map for my function. I will delete this index here to make a cleaner map. And now I'm interested in calculating just the sum of products. So I will not write the zeros just to make the map more clear, but we may have them there. So now every place in the map is a minterm. This is minterm 0, this is minterm 1, and it's easy to convert the minterm to the expression. For example, this minterm here is the minterm that is 1 when variables a, b, c, and d are 1, 0, 0, 1. It means that a must be 1, b must be 0, c must be 0, d must be 1. So to have a minterm 1 in this case, I need to complement b and complement c. Okay, so make it 1 when it's 0, it's 1, sorry, 0, 0, 1. So I can, from here in the map, it's easy to see the minterm and the expression corresponding to any minterm. Now, when I simplify two minterms, for example, these two, this minterm will be A, B complemented, and CD. Okay, I can simplify these two minterms. I can apply the reduction theorem, because these minterms only differ in one literal. In this case, they differ in literal C only. Okay, it's easy to see because they only differ here in the expression in this literal. But it's easy to see in the Carnot map also because we sort the values like in the gray code. It means that I sort the values so that from one place to the adjacent place only one bit changes. It means that these two minterms, from this minterm to this minterm, only one literal changes. these minterms are said to be adjacent. Okay, so because I know they are adjacent, I know that I can simplify them. If I do it algebraically, it gives A, B complemented D. This is a term which is 1 when A is 1, B is 0, and D is 1. C is not in the term anymore, so no matter what the value of C is. Okay, but this term is also easy to see in our map. If we pay attention to the map, this group of ones here corresponds exactly to this term, the term formed by adding together these two minterms, because this is all the places in the map which are 1 exactly when A is 1, B is 0, and D is 1, no matter what the value of C is. Okay? So in fact, I can forget about all this algebraic calculation, and if I see two ones that are adjacent in the map, I just can combine them into an implicant, into a first order implicant, okay? Just as I do algebraically. It's also important to remember that in a Carnot map, all the adjacent places are actually adjacent minterms, but adjacencies also go beyond the border. So this position here is adjacent to this position here, because they only differ in 1 bit. Okay, so the map is cyclic in the horizontal and in the vertical direction. So it's important to understand what are the adjacent places in the map. So taking all this into account, we have seen that it's easy to find the implicants of by combining minterms. Okay, but the same thing I can do with other terms. As we have seen, this term here is A, B complemented D. Okay, but we can see that we have another term here. These two places together will correspond to another term. Okay, actually this term is we can see it's the term that is 1 when A is 1, B is 1, so it's A, B, and when D is 1, B, D. These two groups in the map are adjacent. They are separated by this line. They are in adjacent columns. It means that the actual terms can be simplified. They only differ in this case in the biliteral. They can be simplified as AD. And AD forms a new implicant. A new implicant corresponds to the places in the map where A is 1 and D is 1. It is all these places here together. Okay? So in the same way, I don't really need to do it with the equations algebraically. Whenever I detect that I have two terms that are adjacent, two groups that are adjacent, I can simply put them together. Okay? So that's the way I graphically find my implicants. When I have a group like this, okay, it may be adjacent to other groups of the same order. It's important that we can only simplify with another term of the same order. This term has two literals. I can only simplify with another term with two literals. It means I can only simplify it with another term that is for a group of four places in the map. Okay, the possibility will be to simplify with a group adjacent to the left. That will be a group like this, but I don't have ones in all these places. Or the group on top. The group on top will be a group of 4 formed by these two places and these two places together, okay, because it's cyclic. I don't have those groups because I don't have ones in my map, so these the term that represents this group cannot be simplified with another adjacent group. I found a term that cannot be simplified anymore. This term represents a prime implicant. Okay? So, once we know how to find the terms in my map, and once we understand the simplification method using the algebraic method, I will go back and do it right away. Okay, there's a lot of things to delete here. And so basically, to do that, I will start finding my prime implicants directly. So for example, here I start with this one. Okay, this one and is adjacent to this one. So here I have one implicant. I will not mark implicants if they are not prime implicants. So I just see in my mind that this is an implicant, and I find adjacent ones. This is an adjacent implicant of the same order. So they form a order 2 implicant. I don't have the corresponding adjacent one, so I know I cannot simplify anymore, as we have already seen. Okay, so this is a prime implicant. This is a simple term that I will use to form my functions. So the idea is, in the first step, I find all prime implicants of the function by going through all the starting with all the mean terms. For example, if I have this mean term together with this mean term, they form an implicant. Okay, this I don't have an adjacent one below. On top of it, I don't have an implicant here, and on the right I don't have another implicant. So it cannot be simplified. So it's a prime implicant as well. Okay. Now this one forms an implicant with this one, in this group. Now I check. There's not a group below, not a group on the right, not a group on the left, so it cannot be simplified anymore. This is another prime implicant. Okay, so there's one left. If you see, this one and this one here is adjacent to this one, but this one here is adjacent to the one on the right, which is this one. So this is two ones with no additional adjacencies, so this is also a prime implicant. Now that I have all my prime implicants, I determine to form my function, like in the algebraic method. Yes, I add as many prime implicants as I need to cover all the mean terms. Some prime implicants are essential. Here they are very easy to see. For example, this prime implicant is essential because it's the only prime implicant covering this one, or this one, or this one. So this is called an essential prime implicant, and this is called a distinguished term, distinguished mean term, because it makes the prime implicant to be essential. So I will have to take this prime implicant for sure, also this prime implicant for sure, because this is the only one covering this one, and with this one and this one I have covered almost all mean terms except this one. Here I have two options. I may take this one on the top, or this one going to the right. Okay, the two are order 1 prime implicants, have similar complexity, the same number of literals, so it's not very important which one I take. So I'll take this one first. Okay, now I'll calculate the expressions for this prime. We already did, but for this prime implicant, this is the term that is 1 when A is 1 and D is 1, so it's AD. This prime implicant is 1 when A is 0, so it appears complemented. when b may have any value, so it doesn't appear in the expression, b may be 0 or 1, c is 0, so it's complemented here, and d is 0, so it's complemented as well. And now if I select to use this one, the expression for this one is a pre-implicant, that is one when b is 0, c is 0, and d is 1. So a minimal expression for my function would be a complemented, c complemented, b complemented, plus b complemented, c complemented, d plus ad. You can compare with the previous example, so you can see that this is the same result we got with the algebraic method. Okay, and that's it.